Right now, somewhere above the clouds, 10,000 Boeing 737s are in the air carrying sleeping passengers who have no idea how the most ordinary machine in the sky quietly became the most extraordinary aircraft ever built. There is a particular kind of stillness that settles over an aircraft cabin just before pushback. The overhead lights have dimmed to a soft amber. The last bags have been stowed. The boarding door has sealed shut with a low, pressurized thud that you feel more in your chest than you hear with your ears. And then it begins, that sound. Low, continuous, vaguely oceanic. A hum that seems to come from everywhere and nowhere at once. Vibrating through the seat cushion, through the armrest, through the soles of your feet where they rest against the carpeted floor. If you want to explore the science of flight, the quiet history of engineering, and the subtle world that surrounds you every time you travel, subscribe to Simple Science. We cover exactly this kind of territory, one calm, curious story at a time. That hum you feel on a Boeing 737 before it moves a single inch is not engine noise in the traditional sense. It is the sound of hydraulic pumps cycling through their startup sequence, fuel pumps pressurizing the wing tanks, and the aircraft's electrical systems pulling power from the auxiliary power unit, the small turbine power unit, the small six-cylinder engine housed in the tail that runs independently of the main engines and keeps the aircraft alive on the ground. Every one of those systems has a distinct vibration frequency. Together, they layer into something that passengers across decades have independently described the same way, like being held. The Boeing 737 is the most produced commercial jet aircraft in history. As of early 2026, more than 12,000 have been built and delivered, a number that puts it ahead of every other commercial aircraft type ever manufactured. Over the course of a single day, roughly 10,000 individual 737 flights take off somewhere in the world. That is, one flight every 9 seconds, every hour, around the clock, including the quiet hours between midnight and dawn, when most people in the departure city are already asleep in their beds. The aircraft that generates this hum, this particular and recognizable presence, has been doing so since April 9th, 1967, when the very first 737 prototype lifted off from Boeing Field in Seattle at 1:15 in the afternoon. The test pilots on that maiden flight were Brian Weigel and Lou Wallach. The flight lasted 2.5 hours. When they landed at Payne Field in Everett, Washington, Weigel radioed back to Boeing with the kind of understatement that test pilots favor. He said, simply, that the airplane was a delight to fly. That prototype, registered N73700, is still around. After its testing career, it was passed to NASA, who used it as a flying laboratory for 30 years. It now sits in the Museum of Flight in Seattle. You can walk around the original 737 today and notice how much smaller it looks than the aircraft you stepped onto at the airport. The fuselage diameter is the same. The basic shape is the same. The hum, in all likelihood, would feel the same. The cabin you are settling into tonight, or wherever you happen to be listening, inherits something from that 1967 aircraft. Not the engines, not the avionics, not the materials, but the geometry. The 737's fuselage cross-section, the circular diameter of the tube you are sitting inside, is 3.76 meters. Boeing set that dimension in 1964 when the program was first sketched out, and they have never changed it. Every 737 that has ever flown, from the first underpowered prototype that landed in Everett to the latest MAX variant rolling out of the Renton factory today, shares that same circular measurement. It is one of the quiet constants running through 60 years of aviation history. For now, though none of that history matters much, what matters is this moment. Low hum underfoot, the slight vibration in the window, the sense of the aircraft gathering itself before the journey begins. Millions of people have fallen asleep to this exact feeling, in this exact seat configuration, under these same softened lights. There is something in that continuity that is worth resting in. The aircraft knows what to do. It has done this more than 300 million times. You can simply let it. In 1964, Boeing was in trouble. It hadn't fully admitted to itself yet. The company had built its reputation on large aircraft. The 707 had transformed transatlantic travel. The 727, a trijet with engines clustered at the tail, was finding its footing on medium-haul routes across the United States. But below those routes, on the shorter legs between smaller cities, Boeing had nothing, and its competitors had already moved. The Douglas DC-9 had entered the market first. It was a rear-engined, narrow-body jet designed specifically for the short-haul segment Boeing had ignored. The French Sud Caravelle had been operating since 1959. The British Bax 111 began commercial service in 1965. These were not theoretical competitors. They were already sitting at gates, already selling seats, already building loyalty with the regional airlines that were quietly becoming the backbone of commercial aviation. Boeing's board approved the 737 program on February 1965. The development budget was set at $150 million, which translates to roughly $1.1 billion in today's money. The sales pitch was straightforward. Big jet comfort on short-haul routes, 6 seats across instead of 5. A wider cabin than any competitor, standard of freight containers that could load into the belly without modification. Jack Steiner was appointed chief engineer. He had already designed the 727, and he brought the same instinct for practical efficiency to the 737. To save time and cost, the team borrowed heavily from the aircraft they already knew. The 737 shared around 60% of its structural parts with the 727. The fuselage cross-section, that 3.76 meter diameter mentioned in the previous chapter, came directly from the 707. This wasn't laziness. It was how Boeing kept the program alive on a budget, while arriving to market as quickly as the competition allowed. Lufthansa placed the first order in February 1965, committing to 21 aircraft worth $67 million. The deal came with a caveat that reveals how uncertain the whole project felt at the time. Lufthansa had insisted before signing on a written assurance from Boeing that the 737 program would not be cancelled. Boeing gave them that assurance. It is a quiet detail that tends to get lost in the later story of the aircraft's extraordinary success, but it matters. At the very beginning, Boeing needed a customer, more than the customer needed Boeing. Lufthansa also shaped the aircraft in a concrete way. Boeing's original specification called for a 60-seat design with a range of around 1,000 miles. Lufthansa told Boeing that 60 seats was not enough. The airline operated routes across Europe with different passenger volumes and needed something closer to 100 seats to make the economics work. Boeing agreed and stretched the cabin. By the time the first prototype rolled out of the factory in December 1966, the 737-100 could seat up to 115 passengers in a single-class configuration. The aircraft that came out of that process was genuinely unusual for its time in one specific way. Every other short-haul jet of the era mounted its engines at the rear of the fuselage. The Caravelle, the DC-9, the 111. All of them had their engines mounted high on the tail section, which kept the landing gear short and the cabin low to the ground. Boeing chose a different path. The 737's engines were placed under the wings, a decision that would define the aircraft's visual identity for the next 6 decades, and that would also create one of its most persistent engineering challenges. But that comes later. The wing-mounted engines produced a wider, more balanced aircraft. They made maintenance simpler because technicians could reach the engines from the ground without ladders or platforms. They moved the weight closer to the center of the fuselage, improving handling, and they allowed Boeing to keep the cabin wider than any competitor, which turned out to be exactly the selling point that airlines needed to hear. United Airlines followed Lufthansa with an order in April 1965, but United wanted something larger than the 737-100 Lufthansa had ordered, a slightly stretched version that became the 737-200. Both variants were in development simultaneously, which meant Boeing was running 2 aircraft programs on one budget, with a team that was, by the standards of any comparable Boeing project at the time, deliberately small. The prototype was assembled not in the gleaming modern facilities Boeing would later use, but in Plant 2 at Boeing Field in Seattle, the same building where the B-17 Flying Fortress and the B-52 Stratofortress had been built before it. The fuselage fit inside, the tail did not. Workers assembled the vertical stabilizer outside the building, in the open air, and then mated it to the rest of the aircraft once the fuselage had been rolled out. It is the kind of detail that feels somehow fitting for a program that was running late, underfunded, and uncertain from its first day. The aircraft that would eventually become the most produced commercial jet in aviation history began its life with its tail sticking out of a factory door in Seattle. The engineers signed off. The prototype moved to the flight line, and Boeing waited to find out whether the gamble had been worth it. The Boeing 737-100 entered commercial service on February 10, 1968, with Lufthansa operating the first revenue flight. By almost any measure, the aircraft's debut should have been the beginning of something enormous. Instead, it was closer to a quiet alarm nobody paid much attention to. Only 30 Boeing 737-100s were ever built. 22 went to Lufthansa 6 to Malaysia Singapore Airlines, and 2 to Avianca in Colombia. That was the entire production run of the original variant. For comparison, the Douglas DC-9, the aircraft the 737 had been designed to beat, was already selling in the hundreds. The 737-100 was too small for most airlines' needs, its range too modest, its cabin capacity too limited to make the economics work across the route networks that carriers actually flew. United Airlines had seen this coming from the beginning. When Boeing came to United with the 737-100, United said it was interested, but wanted something bigger. Boeing stretched the fuselage. The 737-200, about 2 meters longer than the 100, first flew on August 8, 1967, just 4 months after the original prototype. United put it into service in April 1968, 2 months after Lufthansa had inaugurated the 100. Both variants were flying commercially within the same year, which was an unusual pace, even by Boeing's standards. The 737-200 sold better. Over the following 2 decades, 1,114 of them were built and delivered, a number that kept the program alive through some genuinely difficult years. But difficult is an understatement. In 1970, Boeing received only 37 total aircraft orders across its entire product line, not just the 737. The company was managing the cost overruns from the 747 program, dealing with a recession, and watching airlines pull back from expansion plans they had made during more optimistic times. Boeing laid off tens of thousands of workers in the Seattle area. A billboard appeared near the city that became famous. "Will the last person leaving Seattle please turn out the lights?" The 737 program specifically came close to cancellation more than once in this period. Facing sustained losses, Boeing considered selling the design to Japanese aviation interests and closing the production line entirely. What kept the 737 alive was a combination of factors. The US Air Force ordering 19 modified 737-200s as T-43 navigation trainers in the early 1970s, a gradual uptick in airline orders as the economy recovered, and the willingness of Boeing's leadership to hold on through the drought rather than cut the line. One detail about those early years stands out. The 737 was the first commercial jetliner to fly with only 2 crew members on the flight deck. Every other jet of the era required a flight engineer as a third person in the cockpit, monitoring systems that 2 pilots could not reasonably watch while also flying the aircraft. Boeing had designed the 737 so that a 2-person crew could handle everything. Airlines found this controversial. Pilot unions pushed back, arguing that removing the 3rd crew member introduced risk. Boeing argued, and ultimately proved, that the aircraft's systems were designed specifically around a 2-person operation, and were actually safer because of the reduced complexity and clearer division of responsibilities. The battle over crew size was one of the more prolonged disputes in commercial aviation history, and it delayed 737 operations with some carriers for years. But Boeing did not budge, and by the time the Classic series arrived in the 1980s, 2-person crews were standard across the industry. The 7737 had set the template that every subsequent narrow-body jet followed. The last 737-100 built, delivered to Malaysia Singapore Airlines in October 1969, would eventually end its career in Peru with a carrier called Aero Continente. Its final revenue service was in 2005, 37 years after its type had entered commercial service. The prototype, N73700, went to NASA after Boeing was done with it, spent 3 decades as a flying laboratory, and eventually came to rest at the Museum of Flight in Seattle, where it sits today. It is a small, slightly cramped aircraft by modern standards. Standing next to it, you would not immediately guess that it was the ancestor of an aircraft that would eventually carry a third of all commercial air passengers on Earth. But the fuselage cross-section is there, and the basic geometry is there, and the two-crew cockpit philosophy is there. The 737 that almost didn't survive the 1970s became the foundation for everything that came after it. Look at almost any short-haul jet built in the 1960s, and the engines are at the back. The Douglas DC-9, the British B-Axi 111, the French Caravelle, all of them mounted their engines high on the tail, far behind the wings, clustered near the fuselage's rear. It was the dominant design philosophy of the era. Rear-mounted engines kept the wings clean and simple. They reduced the noise passengers heard in the cabin. They worked well. The Boeing 737 did something different. Its engines sit forward, under the wings, close to the ground, and the reason for that specific placement is a story that runs from a single design decision made in 1964 all the way to the shape of the aircraft you fly on today. When Boeing designed the original 737, one of its core goals was accessibility. The aircraft was intended to serve smaller airports, many of which, in the late 1960s, lacked the infrastructure that large hub airports took for granted. No jet bridges, often no tall mobile stairs, no heavy equipment for engine servicing. Boeing wanted an aircraft that ground crews could work on using standard tooling, without platforms or elevated ramps. To do that, the aircraft needed to sit low to the ground, and to sit low to the ground, the landing gear had to be short. Short landing gear created a problem. The original Pratt & Whitney JT8D engines that powered the first 737s were small enough, in cross-section, to fit under the wing with just enough clearance above the tarmac. But even then, the engines could not hang beneath the wing in the conventional way, with a long pylon dropping them down from the leading edge. There was not enough room, so Boeing mounted the engines further forward on the wing, ahead of the leading edge rather than beneath it, and tucked them up as close to the wing as possible. The result was a distinctive silhouette. Engines that look as if they are sitting on top of their own small shelves, pressed against the underside of the wing rather than hanging freely below it. This worked for the original 737 and through the classic series that followed in the 1980s. But when Boeing developed the next generation series in the 1990s, airlines wanted more fuel-efficient engines. More fuel-efficient engines meant larger fan diameters. Larger fans needed more ground clearance. The 737's short landing gear still hadn't changed, so Boeing's engineers had to find another way. The solution was engineering of the kind that looks odd from the outside, but is quietly elegant once you understand it. Boeing moved the engines even further forward on the wing and slightly higher. They also changed the shape of the engine nacelle itself, the outer housing that surrounds the fan and core. Instead of a perfectly circular cross-section, they flattened the bottom of the nacelle. The resulting shape is sometimes called the hamster cheek profile, a slightly squashed oval that provides just enough ground clearance for the larger fan to clear the tarmac, while the short landing gear stays intact. This flat-bottomed nacelle became one of the most recognizable visual features of the 737 Next Generation series, the aircraft flying most commercial routes today. It is not beautiful in the way that a perfectly symmetrical round engine is beautiful, but it is a precise solution to a precise problem. Every time you look at the engine pod on a 737 and notice the slightly flattened underside, you are seeing 6 decades of engineering compromise made visible in a single curve. The low ground stance that produced all of this originated in a practical concern about baggage handlers and maintenance technicians working at small airports in 1964. A mechanic checking an engine oil level on the original 737 could reach the relevant access points from the ground, standing upright, without any equipment. Catering trolleys could pull directly up to the aircraft doors. Baggage loaders did not need belt conveyors. The low profile of the aircraft meant that the entire ground operation could run faster and with fewer resources. This mattered enormously for the economics of short-haul flying. A 737 on a busy domestic route might turn around at the gate in under 30 minutes, refueled, cleaned, catered, and reloaded with new passengers before pushing back for its next departure. That 30-minute window depended entirely on the aircraft being low enough for ground crews to move around it efficiently. The engine position was not separate from that logic. It was part of it. The 737's design has carried this original low stance through every subsequent generation, and it continues to shape the aircraft today. Boarding stairs instead of jet bridges, fast turnarounds at regional airports, maintenance accessible from the ground. These were the promises Boeing made to airlines in 1965, and they were encoded in the short landing gear and the forward-mounted engines that came from that promise. The aircraft's distinctive look, the flat-bottomed engines, the low belly, the compressed geometry, all of it traces back to a decision about where to put the wheels. There is a particular frequency range in which the human body stops resisting and begins to settle. It is not a silence, and it is not music. It is something closer to a continuous, low-frequency pressure. A sound you feel more in your chest and legs than you process through your ears. The hum of a commercial aircraft cabin at cruise altitude sits inside this range. And it is one of the reasons people fall asleep on planes so reliably, often within minutes of reaching cruising altitude, in conditions that would normally keep them awake. Aircraft cabin noise is not a single sound. It is a layered environment, built from multiple sources running simultaneously. The engines contribute a broad spectrum rumble, with the dominant energy concentrated in the lower frequencies. Roughly, between 50 and 500 Hz during cruise. The airflow over the fuselage adds a white noise component, a high-frequency rushing that fills in the upper registers. The environmental control system, the pressurization, and air conditioning machinery that keeps the cabin livable at altitude adds its own steady undertone. Together, these sources create a sound environment that is dense, consistent, and non-threatening, with no sudden changes in pitch or volume to trigger the brain's alertness response. Research on aircraft cabin acoustics has established that the dominant low-frequency components in jet aircraft cabins, particularly below 500 Hz, are the frequencies least effectively attenuated by the fuselage structure. They pass through the cabin wall relatively freely and fill the interior space. This is the energy you feel in your seat, in the window glass, in the floor under your feet. It is not loud in the conventional sense, but it is pervasive. It surrounds you completely. And because it is consistent rather than variable, the brain's auditory processing system gradually classifies it as background and reduces its attention to it. The technical term for this is habituation. The practical result is that your brain quiets down. The Boeing 737 Next Generation series, which includes the 737-800 that flies the majority of short and medium-haul routes globally, is powered by CFM International CFM56-7 engines. These engines were designed with a high bypass ratio, meaning a large proportion of the air they move passes around the core rather than through it. This design produces thrust more efficiently than older engines, but it also shifts the noise profile toward the lower frequency ranges. The large fan at the front of the engine moves massive quantities of air slowly, and slow-moving air generates lower frequency sound than the fast-moving, high-pressure exhaust of older turbojet designs. The 737N's cabin acoustic environment is dominated by this low rolling frequency, and it is one of the reasons the aircraft is considered quieter and more comfortable than the generations that preceded it. Boeing's acoustic engineers work on cabin sound environments as a specific design discipline. The goal is not to eliminate noise, which is not achievable at 35,000 feet in a metal tube moving at 900 kilometers per hour, but to shape the noise into a profile that passengers experience as neutral or even pleasant. This involves controlling which frequencies are attenuated by insulation and which are allowed to pass through, managing the resonant characteristics of the cabin interior, and ensuring that the overall sound level stays below the threshold at which prolonged exposure causes fatigue or stress responses. The standard measure is decibels, a weighted, which weights the measurement toward the frequencies the human ear is most sensitive to. A typical 737 cabin at cruise sits at around 75 to 80 dBA, which is roughly equivalent to the sound level inside a busy office, but spectrally very different. The difference between an office and an aircraft cabin at cruise is not volume. It is consistency. Office noise is variable, punctuated by speech, phone calls, movement, sudden sounds. Aircraft cabin noise is steady. It does not change between 1 minute and the next. And this consistency is, paradoxically, one of the most relaxing acoustic environments the human brain encounters in everyday life. The brain's threat detection systems are primed to respond to change, not to steady-state conditions. A consistent sound, once habituated, disappears from conscious awareness entirely. The hum becomes silence of a sort. The reason white noise machines and sleep apps built around rain, ocean waves, and fan sounds work is not that these sounds are inherently calming. It is that they are consistent enough to mask variable, attention-grabbing sounds, and in doing so, they give the brain permission to stop monitoring its environment. A 737 at cruise altitude does the same thing with its entire acoustic environment. The engine hum, the air noise, the system undertone. Together, they form a masking layer that covers the small, variable sounds that would otherwise keep you partially alert. Your brain stops trying to pass the environment and lets go. This is the quiet engineering reason why millions of people across decades of air travel have described the experience of being on a 737 the same way. Not the food, not the seats, not the destination, the sound, the feeling of being surrounded by something steady and continuous that doesn't need anything from you. The aircraft holds all of it, and you don't have to listen for what comes next. At any given moment, while you are reading or listening to this, there are roughly 1,250 Boeing 737s airborne somewhere in the world. Not in total, not across a whole day. At this specific moment, right now, over the course of a full day, the global 737 fleet operates somewhere in the region of 10,000 flights. One departure every 9 seconds, every hour, around the clock, including the quiet hours between midnight and dawn, when much of the northern hemisphere is asleep. That number requires a moment to sit with. It is not the total for a week or a month. It is a daily figure. It means that across the time you spend sleeping tonight, roughly 20,500 to 3,737 flights will take off and land somewhere in the world. While you are unconscious in your bed, the aircraft is working. The scale of 737 operations becomes more concrete when you look at the operators. Southwest Airlines in the United States operates exclusively Boeing 737s, one of the largest single-type fleets in commercial aviation history. At its peak before the pandemic, Southwest was operating more than 750 737s, with departures running from early morning to late night across hundreds of American cities. Ryanair in Europe similarly operates a fleet built entirely around the 737, with over 500 aircraft serving routes across the continent. Each of these carriers alone generates more daily 737 flights than many national airlines produce in total. The aircraft's dominance in short and medium-haul flying reflects decisions made early in the program's history, but also a structural reality about commercial aviation. The vast majority of airline passengers do not travel between major international hub cities. They travel between regional cities, between secondary markets, on routes of 2 or 3 hours rather than 12. These routes require an aircraft that is economical to operate with load factors that are not guaranteed to be high, that can turn around quickly at gates without extensive servicing, and that can do this repeatedly across a day without accumulating maintenance issues. The 737 was designed for exactly this, and it has continued to be refined for exactly this across 6 decades. The cumulative flight total across the entire 737 family since the first revenue service in February 1968 now exceeds 300 million flights. This number is difficult to fully comprehend. If you stacked 300 million flights end to end, assuming an average flight duration of 2 hours, you would have roughly 600 million hours of commercial aviation. That is more than 68,000 years of continuous flight, aboard a single aircraft type. Within those 300 million flights, the variation is enormous. Some 737 routes are under 30 minutes. Short hops between island communities, connections between cities separated by a mountain range that makes road travel impractical. Others are close to the aircraft's range limit, 6 or 7 hours in the air, crossing sea stretches or continental regions that would otherwise be inaccessible to narrow-body operations. The 737 has flown from Norwegian coastal cities to Spanish beach destinations, from Alaskan bush communities to the lower 48 states, from island chains in the Pacific to mainland hubs with connecting traffic for long-haul aircraft. The 12,486 aircraft built as of early 2026 are distributed across airlines in every region of the world. Some are new, delivered to carriers within the past few months from Boeing's factory in Renton, Washington, where 737s have been assembled since 1970. Others are old, carrying maintenance logs that run to thousands of pages and flying routes they have flown hundreds or thousands of times. An individual 737 airframe, well maintained, can accumulate more than 50,000 flight cycles over its operational life. A flight cycle is one takeoff and one landing. 50,000 cycles on a single aircraft means 50,000 separate departures and arrivals, 50,000 pressurization and depressurization events, 50,000 landings absorbed through the undercarriage and transmitted through the structure. The aircraft that carries you on a 2-hour regional flight may have done exactly this kind of work every single day for 20 years. The maintenance records would show it. Every cycle logged, every inspection completed, every component replaced at its scheduled interval. The 737 is not glamorous in the way that a wide-body, long-haul aircraft is glamorous. It does not carry passengers across oceans or park at gates designed around its large windows. But it moves more people more often between more places than any other aircraft in history. That is the quiet fact underneath the hum. Every flight is one of 10,000 for the day. Every passenger is one of hundreds of millions carried in a year. And somewhere, right now, another 737 is pushing back from a gate in a city you might never visit, carrying people to places you might never see, doing the same ordinary and extraordinary work it has done every day for nearly 60 years. Within minutes of reaching cruising altitude, the pilots of a Boeing 737 typically do something that most passengers would find surprising if they watched it happen. They stop flying the aircraft by hand The autopilot engages with a button press on the mode control panel, a small panel on the glare shield above the primary flight displays. From that moment, the aircraft's flight management system takes over the physical task of flying, maintaining the selected altitude, following the programmed route, holding the correct speed, and making the thousands of small corrections to pitch, roll, and yaw that keeping a 160,000 pound metal tube in stable flight at 35,000 feet requires every few seconds. The pilots monitor. They communicate with air traffic control. They watch the weather, manage the fuel state, brief the descent profile, and run the checklists that structure each phase of flight. But the physical act of flying, the continuous, precise, mechanical task of keeping the aircraft where it is supposed to be, belongs to the automation for most of the journey. On a typical 2-hour domestic 737 flight, pilots may fly manually for a total of fewer than 10 minutes. The first few minutes after takeoff, before the autopilot engagement altitude is reached, and the final approach and landing, when the aircraft is hand-flown back to the runway. Everything between departure and descent is automated. This is not complacency, and it is not laziness. It is the design of the system working as intended. The Boeing 737's flight management computer can hold altitude to within a few feet, maintain a course to within fractions of a degree, and respond to changing atmospheric conditions faster and more precisely than human hands can manage over an extended period. The automation is better at the steady-state task of cruise flight than any pilot is. And pilots who try to fly the cruise portion manually over a long flight introduce more variation in altitude and heading than the system would produce. The 737's autopilot system, as fitted to the next generation and MAX series, is a 3-axis system, meaning it controls the aircraft in pitch, roll, and yaw simultaneously. It works in conjunction with the autothrottle, which manages engine thrust to maintain the target speed, and the flight management system, which holds the programmed route and makes decisions about when to climb or descend based on air traffic control clearances that the pilots have entered. These systems communicate with each other continuously, negotiating between altitude, speed, and route requirements in real time. The Boeing 737's cockpit philosophy follows what the industry calls the dark and quiet principle. A well-run cockpit at cruise should have very few active sounds and very few illuminated warning lights. The absence of alerts is the signal that everything is normal. Systems are designed to require no input from pilots unless something needs attention, and the hierarchy of alerts, from quiet advisory chimes through caution tones to urgent warning sounds, is structured so that the most serious conditions produce the most unmistakable response. In practice, on a routine flight, the cockpit can be calm and relatively silent for extended periods. The loudest thing is often the hum of the engines and the sound of 2 pilots breathing. This design philosophy has a direct effect on the passenger experience, even though passengers never see the cockpit during cruise. A calm cockpit means calm decision-making. Calm decision-making means smooth, unhurried transitions between phases of flight. The descent profile is programmed and executed gradually, Speed reductions happen in incremental steps. The aircraft does not suddenly change configuration or attitude because someone has been startled or rushed. Everything that happens at the front of the aircraft flows through to the back as a smooth, continuous experience, punctuated only by the sounds of flaps extending or landing gear deploying, sounds that have their own reliable rhythm. The autopilot will fly the 737 as long as it is needed. It does not get tired, does not lose concentration, does not have moments of inattention in the middle of a long cruise segment when there is nothing unusual to engage with. It holds its altitude and its course and its speed with the same precision at the 2-hour mark as it did at the 10-minute mark. The pilots remain responsible for the flight and ready to take over at any moment. But the automation carries the aircraft through the quiet middle hours of the journey, while passengers below recline their seats and close their eyes. You are, in the most literal sense, being carried, not by effort and attention paid second by second to the physics of flight, but by a system that has been designed to hold you steady without interruption. The autopilot is working. The flight management computer is working. The aircraft knows where it is going, and it knows how to get there. Whatever else is in your mind right now, the aircraft has the rest of it. One of the more counterintuitive facts about flying in a commercial aircraft is that the air inside the cabin is, by measurable standards, cleaner than the air in most of the buildings you spend your time in every day, cleaner than the average office, cleaner than a shopping centre, in some assessments approaching the cleanliness of a hospital operating room. This seems implausible when you consider that you are sharing the cabin with 150 strangers in a metal tube with no windows that open. But the numbers bear it out, and the system responsible for it is one of the less discussed engineering achievements built into the Boeing 737. Cabin air on a commercial aircraft is not simply recirculated. It is a blend of two sources: fresh air drawn directly from outside the aircraft and filtered recirculated air. On the 737 and most modern narrow-body jets, approximately 50% of the cabin air supply comes from outside the aircraft at any given moment. This outside air is extracted from the engine compressors, a process called bleed air extraction. The air enters the engine at the front, where it is compressed to very high pressure and temperature, sometimes exceeding 200 degrees Celsius. It is then routed through an air conditioning pack that cools it, adjusts its humidity, and pressurizes it to cabin levels before delivering it to the overhead distribution system. Fresh, compressed, processed air from outside the aircraft arrives in the cabin continuously throughout the flight. The other 50% is the recirculated portion, and this is where the HEPA filtration comes in. HEPA stands for High Efficiency Particulate Air. Commercial aircraft use filters that meet the aerospace industry standard of 99.99% minimum removal efficiency for particles. These are the same class of filters used in hospital intensive care units and surgical theatres. They capture particles as small as 0.1 microns, which is smaller than most bacteria and most virus particles. The air that passes through these filters on its way back into the cabin has had virtually everything biological removed from it. The entire volume of air in the cabin is replaced through this combined fresh air and filtered recirculation system. Every 2 to 3 minutes. At cruise altitude, this gives you roughly 20 to 30 complete air exchanges per hour. For comparison, a standard office building typically aims for 6 to 12 air exchanges per hour, and many older buildings achieve fewer than that. The aircraft's ventilation rate is more aggressive than almost any indoor environment you occupy in daily life, by a significant margin. The airflow pattern inside the cabin is also designed to minimize the lateral spread of contaminants. Air enters the cabin from overhead nozzles and flows downward toward floor-level exhaust ports near the bottom of the fuselage sides. This vertical, top-to-bottom flow pattern means that air from your immediate area moves downward and out, rather than forward or backward along the aisle where it would pass other passengers. The effective airspace that a given passenger shares with other passengers in terms of breathing the same air is largely limited to the 2 or 3 rows immediately adjacent to their seat. The cabin air environment, despite appearances, is divided into relatively contained ventilation zones. There is a detail in this system that tends to get overlooked. The air that comes in as bleed air from the engines is, at the altitude the aircraft cruises, almost completely sterile. At 35,000 feet, the outside air contains virtually no biological material. There are no bacteria, no mold spores, no pollen, no particulate pollution from human activity at ground level. The air at that altitude is thin, cold, and biologically empty. The 737's environmental control system takes this already clean air, processes it, and delivers it into the cabin. Then, it takes the cabin's used air, runs it through HEPA filters, and blends it back in. From a biological contamination standpoint, the inputs to the cabin air system are extremely clean. The practical result is a breathing environment that compares favorably to almost anywhere else you will spend time during the day. The air is dry, which is its own discomfort, because the moisture content of air at high altitude is very low, and the blending process does not add much back. This dryness is why people drink water on flights, and why their eyes feel dry after several hours. But the particulate cleanliness is genuine, and it is backed by the FAA's requirements for aircraft manufacturers to demonstrate that the ventilation system provides clean air free from harmful concentrations of contaminants under normal operating conditions. The aircraft is doing something quietly remarkable in maintaining this environment. It is taking the emptiness of the upper atmosphere and turning it into a livable space, renewed every few minutes, filtered to hospital standards, delivered silently from the overhead nozzles above your seat. You are breathing air that 2 minutes ago was 40 kilometers of empty sky. When a Boeing 737 reaches cruising altitude and the cabin pressure stabilizes, something happens inside your body that you are probably not aware of. Your blood oxygen saturation, the percentage of hemoglobin in your blood that is carrying oxygen, drops slightly, not dramatically, not dangerously, but measurably. And this small, quiet, physiological shift is one of the reasons you feel the way you feel on a long flight. Commercial aircraft do not fly at ambient atmospheric pressure. At 35,000 feet, the outside air pressure is roughly a quarter of what it is at sea level, which is not survivable without a pressurized environment. The 737's fuselage is pressurized to maintain a cabin environment equivalent to what you would breathe at an altitude of 6,000 to 8,000 feet above sea level. The specific figure varies slightly by flight altitude and aircraft configuration, but the standard regulatory maximum is 8,000 feet equivalent, and most flights maintain cabin pressures comfortably within that range. At a cabin altitude equivalent of 6,000 to 8,000 feet, the partial pressure of oxygen in the air you are breathing is lower than at sea level. There is still 21% oxygen in the air, the same as everywhere on Earth. But the total air pressure is lower, which means there are fewer oxygen molecules in each breath. Your lungs absorb slightly less oxygen per breath than they would on the ground. Your blood oxygen saturation, which typically sits at 96 to 99% at sea level in a healthy adult, may fall to between 93 and 96% during a flight. This mild reduction in blood oxygen is technically a form of hypobaric hypoxia, altitude-induced low oxygen. But at these levels, it produces no symptoms in healthy passengers beyond a modest physiological response. That response includes a slight increase in breathing rate and heart rate as the cardiovascular system compensates for the reduced oxygen availability, and a subtle increase in fatigue. Peer-reviewed research published in scientific journals has documented this fatigue response clearly. Passengers on flights where cabin altitude was maintained at higher equivalent altitudes reported more fatigue and discomfort than those on flights at lower equivalent cabin altitudes, even when controlling for other variables, including flight duration and time of day. The body is quietly working harder to maintain its oxygen supply, and that quiet extra effort has an accumulating cost over the course of a flight. Drowsiness is part of that cost, and it is a reliable one. The mild hypoxia of cruise altitude does not put you to sleep in the way that a strong sedative would, but it creates conditions in which sleep comes more easily than it would on the ground. The body's systems are operating at a slightly reduced level of efficiency. The brain is receiving marginally less oxygen than usual. The threshold at which fatigue tips into sleep is lower than it would be in a fully oxygenated environment. This is not a safety concern, because the reductions involved are well within the range the body handles easily, but it is a real physiological contributor to the near-universal experience of drowsiness at altitude. The dimmed cabin lights that airlines use during night flights and long-haul services reinforce this effect through a separate mechanism. The human circadian system is regulated substantially by light exposure. Bright light suppresses melatonin production and signals wakefulness. Reduced light does the opposite. A darkened 737 cabin at cruise altitude, with its engine hum, its mild altitude hypoxia, its consistent temperature, and its steady vibration, creates a convergence of physiological cues that all point toward the same state: rest. Boeing's newer aircraft, beginning with the 787 Dreamliner use fuselage materials that allow cabin pressure equivalent to 6,000 feet rather than 8,000, reducing the hypoxic load on passengers and resulting in measurably better reported comfort on long flights. The 737 cannot achieve this because its aluminium fuselage does not handle the same pressure differential as the composite structure of the 787. But the 737's cabin altitude, sitting comfortably within the 6,000 to 8,000 foot range on most flights, still produces the quiet physiological shift that millions of passengers experience as that particular heaviness that comes over them somewhere around the second hour of a flight. Your body is not failing. It is not struggling. It is making a small automatic adjustment to a slightly thinner environment, and in doing so it is creating the conditions for rest. The altitude is helping you let go. The aircraft carries that effect as part of its operating environment, built into the physics of pressurized flight, and it has been delivering this specific kind of tired to every passenger who has ever sat in its cabin since February 1968. A Boeing 737-800 sitting empty at the gate, with no passengers, no cargo, no fuel, and nothing aboard except the aircraft itself and its permanent equipment, weighs approximately 41,000 kilograms. That is the operating empty weight. The baseline mass of the airframe, engines, flight deck systems, cabin furnishings, and all the fluid systems charged and ready, but with tanks empty, at maximum takeoff weight, fully loaded with passengers, bags, cargo, and fuel. The same aircraft tips the scales at just over 79,000 kilograms. Between the empty aircraft and the fully loaded one, you have added nearly 38,000 kilograms, roughly the equivalent of 190 average adults, all their luggage. The fuel needed to fly several hours, and whatever freight is riding in the belly hold, 79,000 kilograms. This number needs to be felt rather than just read. It is just under 79 metric tons, approximately the weight of 13 adult elephants, or a fully loaded semi-truck fleet of 35 vehicles. And it is going to leave the ground. In a few minutes, it will be cruising at 35,000 feet, at 900 kilometers per hour, held up by nothing except the pressure difference across two wings with a combined span of 34 meters. The wings themselves on the 737-800 span 34.32 meters from tip to tip. They are built primarily from aluminium alloy, with some composite elements in the control surfaces and fairings. In ground configuration, the wings appear rigid. They look like fixed, immovable structures, the kind of geometry that suggests solidity rather than flexibility. But at takeoff weight, under the aerodynamic loading of flight, the wings do not behave like rigid structures. They flex. At cruise altitude, under the upward aerodynamic lift forces generated by the wings, the wingtips of a 737 sit higher than they do on the ground. The exact amount of upward flex varies with load and speed, but the wing is designed to bend, and this bending is intentional. A completely rigid wing would transfer every gust, every variation in aerodynamic pressure directly into the fuselage and into every seat in the cabin. A wing with designed-in flexibility absorbs these variations, smoothing the ride for everyone aboard. The flex is part of the comfort engineering, not a sign of structural inadequacy. The 737 Next Generation series introduced a redesigned wing compared to the classic generation. The NG wing has a larger area, a greater sweep angle, and blended winglets on most aircraft. The upward curving tip extensions that are now standard features on commercial narrow bodies. These winglets were developed in collaboration with aviation partners Boeing and entered service on the 737-800 in 2001. They work by reducing the strength of the vortex that forms at each wingtip as the high-pressure air beneath the wing spills over to the low-pressure region above it. This vortex is a direct consequence of generating lift and cannot be eliminated, but the winglet redirect some of the energy in it into useful forward thrust rather than pure drag. A typical Southwest Airlines 737-700 equipped with blended winglets saves approximately 100,000 gallons of fuel per year, compared to the same aircraft without them. That figure, from NASA's spin-off program, was documented for the blended winglet technology across the fleet. Everything about the weight and structure of the 737 is balanced against everything else. The heavier the aircraft, the more lift the wings must generate, which means more drag, which means more thrust, which means more fuel, which means more weight. Engineers navigate this loop at every stage of design. Every kilogram saved somewhere creates a cascade of smaller savings everywhere else. In 2008, Boeing began offering carbon brake packages for the 737 NGs that reduce the brake assembly weight by up to 320 kilograms per aircraft. That 320 kilograms removed from the undercarriage translated to a 0.5% reduction in fuel burn over the aircraft's operating life, which across a large fleet amounts to millions of litres of fuel annually. The 79,000 kilograms you travel in is the result of thousands of these calculations layered on top of each other. Every panel, every fastener, every litre of fluid in the hydraulic systems, every seat cushion, every overhead bin has been weighed and considered against every other component. The aircraft is as light as it can be, while still being as strong as it needs to be, and the balance point between those two demands has been refined. Across 6 decades of production, right now, if you are on a 737, most of that weight is at rest in your seat, carried by the wings, held by the pressurization, moving through the air at nearly the speed of sound. The aircraft takes all of that mass and makes it, briefly, effortless. While you sleep somewhere above the clouds, there is a person in a darkened room looking at a radar screen, and your aircraft is a small green dot on it. Air traffic controllers do not fly. They do not move. They sit at radar consoles, wearing headsets, watching the sky as a 2-dimensional representation of blinking symbols, each one a real aircraft carrying real people, and their entire job is to ensure that none of those symbols ever touch. The separation standards they maintain are precise. In controlled en route airspace, aircraft flying at the same altitude maintain a minimum horizontal separation of 5 nautical miles which is just over 9 kilometers. Vertically, within the reduced vertical separation minimum airspace that covers altitudes between 29,000 and 41,000 feet, where most 737s cruise, the minimum vertical distance between aircraft is 1,000 feet. These numbers sound comfortable until you consider the speeds involved. A 737 at cruise covers roughly 250 meters every second. A separation of 5 nautical miles at that speed represents about 37 seconds of flying time between one aircraft and the one ahead of it on the same track. The controller does not maintain these separations by watching and reacting. The system is built around prediction. The controller knows the speed, altitude, heading, and route of every aircraft in their sector, fed continuously from radar returns and flight plan data. They calculate conflicts before they materialize, issue instructions to climb, descend, or adjust speed, so that by the time 2 aircraft would potentially conflict, one of them has already been moved. The intervention happens minutes in advance of any actual proximity. The aircraft never gets close enough to the threat for the crew to see it. Air traffic control, as a profession, exists in direct proportion to the growth of commercial aviation. In the earliest years of airline flying, traffic levels were low enough that separation was managed largely by time. Aircraft were assigned departure times and altitude bands that kept them apart by schedule as much as by monitoring. Radar made continuous tracking possible from the 1950s onward, and as traffic volumes grew through the jet age, the staffing of control centers grew with it. Today, the United States alone has more than 14,000 FAA-certified air traffic controllers, working in 21 en route centers, more than 150 terminal facilities, and dozens of oceanic control positions that manage traffic over the Atlantic and Pacific, where radar coverage ends and position reporting takes over. Over the ocean, beyond the reach of land-based radar, a different system applies. Aircraft report their position to control by radio at regular intervals, and controllers maintain separation using these position reports, rather than continuous radar tracking. The vertical separation minimum over oceans reverts to 1,000 feet in RVSM-approved airspace, but the horizontal separation grows substantially to account for the uncertainty in position reporting. This is one of the reasons oceanic crossings still feel slightly different to pilots. There is more space between aircraft and more reliance on the integrity of the position data. The workload of an air traffic controller varies enormously with traffic volume, weather, and sector complexity. A high traffic sector near a major hub airport during the morning push can have a controller managing 15 or 20 aircraft simultaneously, each with its own speed, altitude, and destination requirements, all of which need to be sequenced into the airport's arrival flow without creating gaps that waste runway capacity or bunching that exceeds the airport's handling rate. A quiet overnight sector on a rural en route frequency might have a controller watching 3 or 4 aircraft crossing their airspace over several hours. The overnight shift is when the 737 fleet is at its quietest. Some aircraft are parked at gates, going through their overnight maintenance checks. Others are still flying red-eye departures from the East Coast heading west, cargo runs between distribution hubs, international flights crossing time zones. The controllers who watch these overnight flights work in the same rooms, at the same consoles, under the same fluorescent light as the ones who managed the morning rush 12 hours earlier. The faces change at shift boundaries. The radar screen does not go dark. There is something quietly remarkable about this invisible layer of attention that overlies every commercial flight. You sleep, the aircraft flies. Somewhere below you, in a building without windows, someone is watching. The Boeing 737 was not designed to cross oceans for most of its history. It was a short to medium haul aircraft, built for the domestic routes, the 2-hour hops, the busy corridors between cities that are close enough to drive, but fast enough to fly. That was the original promise. Short runways, quick turnarounds, regional markets. But aircraft, like all technologies, tend to grow beyond their original brief. The Boeing 737 MAX 8, the current production variant that has been entering airline fleets since 2017, carries a maximum range of approximately 3,550 nautical miles. That is 6,570 kilometers. For context, the direct distance between New York and London is approximately 3,000 nautical miles. The distance between the east coast of the United States and the west coast of Ireland is around 20,800 nautical miles. A 737 MAX 8 can, under the right conditions, fly these routes, and some airlines are beginning to do exactly that. WestJet, the Canadian carrier, began operating 737 MAX 8 service across the Atlantic in recent years. The routes that were once reserved exclusively for wide-body aircraft, 767s and A330s, with their dual aisles and large fuel tanks and long-haul interiors, are being served by aircraft that would not look out of place on a domestic shuttle. The economics are the reason. A narrow-body aircraft costs less to operate per seat than a wide-body on the same route, as long as there are enough passengers to fill it. On thinner transatlantic routes, where a wide-body would fly half empty, a 737 MAX makes more sense. Flying at night over water in a narrow-body aircraft is a particular kind of experience. The ocean below is invisible. The darkness outside the window is absolute. No city lights, no coastline glow, nothing but black sky above and a black sea below. The aircraft travels through this darkness for hours, crossing time zones, moving from one continent toward another without any visible landmarks. Inside the cabin, the overhead lights are off. The window shades are drawn on most rows. The only light comes from scattered reading lamps and the faint glow of screens. The engine hum continues exactly as it did over land. The aircraft does not know the difference. What changes is the regulatory environment. Over the ocean, beyond radar coverage, pilots report their position to oceanic control at fixed intervals using HF radio or satellite data link systems. The aircraft navigates by GPS, with inertial reference systems as backup, cross-checking its position continuously. The flight management computer knows exactly where the aircraft is, to within a few meters, regardless of whether any ground station can see it. This precision is one of the achievements of the past 3 decades of avionics development. Ocean crossings that once required careful dead reckoning navigation over featureless water are now executed with the same confidence as a radar-monitored domestic flight. On an overnight transatlantic 737 service, the pilots manage their rest according to regulations that govern crew rest on extended operations. Flights exceeding certain duty time limits require augmented crews or rest provisions. The aircraft flies through the small hours in near darkness, one pilot at the controls, while the other manages communications and systems, and the passengers below are mostly asleep, their bodies adjusting to the time zone they are leaving and the one they are approaching. The 737 MAX 8's range of 3,550 nautical miles means it can reach these transatlantic sectors, but with limited margin. Payload must be managed carefully. Fuel reserves must be calculated against alternates. Headwinds over the North Atlantic, which can exceed 100 knots at certain times of year, consume reserve fuel rapidly and can make the difference between a viable routing and one that requires a fuel stop. This is why the same route is flyable in some seasons and not others, and why airlines publish these services with careful attention to seasonal scheduling. The aircraft that began its life serving short European hops for Lufthansa in 1968, crossing between German cities in under an hour, is now crossing the same ocean that the first transatlantic airliners crossed in the 1930s. The geometry of the fuselage is the same. The diameter of the cabin, 3.76 meters, is unchanged from the original 737-100. Inside that familiar cross-section, passengers sleep their way across the dark water, trusting a machine that was never meant to go this far. And going anyway. The Boeing 737 cockpit at cruise altitude on a routine flight is quieter than most people imagine. There is the engine noise, lower and more muffled through the cockpit insulation than it is in the cabin behind. There is the occasional transmission from air traffic control, a clipped voice delivering a frequency change or a traffic advisory, answered in the same measured tone by whichever pilot is on the radio. There is the sound of the auto throttle making small adjustments. A faint mechanical click as the thrust levers move fractionally to maintain the selected speed. And then, for extended periods, there is very little else. This is not accidental. The Boeing 737 cockpit is designed around a principle that the industry calls dark and quiet. The idea is simple. A cockpit in which everything is working correctly should require no active input from the pilots and should produce no sound or illuminated warning lights that demand their attention. Alerts are hierarchical. An advisory condition, something the crew should be aware of, but which requires no immediate action, produces a single chime and illuminates an amber caution light. A caution condition requiring pilot awareness and possible action produces a distinct tone and a brighter amber indication. A warning condition requiring immediate action produces a loud, distinctive sound that cannot be confused with anything else, and a red warning light. In practice, on a routine flight, the cockpit produces none of these sounds for the vast majority of the journey. Takeoff and initial climb involve a series of call-outs and checklist items. The departure briefing and SID-D clearance are reviewed before pushback. After climb out, as the aircraft levels at its cruising altitude and the autopilot settles into its management of the flight, the workload reduces substantially. The pilots monitor the flight management system's progress along the route, manage any required communications with ATC as the aircraft transitions between sectors, and watch the weather radar for any deviations that might be needed. But the cockpit itself is mostly quiet. This quiet is actively managed. Both pilots wear headsets with noise-attenuating ear cups that reduce the background engine noise to a manageable level, allowing normal-voiced conversation. The interphone system, which connects the cockpit to the cabin crew stations, uses a specific chime pattern that distinguishes it from ATC calls or system alerts. Pilots develop an acute sensitivity to the sound environment, the way a variation in engine tone or an unexpected system sound registers immediately, even after hours of steady-state conditions. This is part of what makes the dark and quiet philosophy effective. When the environment is normally quiet, any deviation from normal is instantly noticeable. The checklist culture in the 737 cockpit structures much of the spoken communication. Boeing provides airlines with standard normal and abnormal checklists, and operators adapt these within defined parameters to match their specific procedures. On a normal flight, the before taxi checklist, before takeoff checklist, climb checklist, descent checklist, and before landing checklist are all called and responded to in a structured call and response format. This structured spoken communication reduces the likelihood of missed items and provides a continuous audio record of what is being done. The rhythm of checklist calls, challenge, and response has a practical quality to it. Specific language, specific sequence, no variation. Between these structured moments, the cockpit conversation on a long cruise segment is often closer to normal human conversation. Pilots share information about the flight, discuss the weather ahead, sometimes talk about previous routes or experience on the same sector. The professional relationship between two people, spending several hours in a small compartment at 35,000 feet, develops its own social texture. There are long silences that are entirely comfortable. There are moments of focused attention when ATC issues a clearance that requires careful readback. There are the quiet minutes when one pilot is calculating something on the FMS and the other is watching the sky. From the passenger cabin, none of this is audible. The pressure bulkhead behind the cockpit door absorbs the sound. The passengers know there are two people at the front of the aircraft, but they hear nothing of what those two people are doing or saying. They hear only the engine hum, the ventilation, and the sounds of their own row. The cockpit conversation happens in its own enclosed world, 20 meters forward of the nearest economy seat, managing an aircraft that requires almost no managing right now. The dark and quiet philosophy means the aircraft is telling everyone aboard, through its silence, that everything is fine. And for the vast majority of the 300 million flights the 737 has completed since 1968, that silence has been correct. Turbulence is the part of flying that people find hardest to let go of. The engine noise, the altitude, the speed. These are abstractions that can be intellectually set aside, but turbulence is physical. It moves your body, it spills drinks, it produces the kind of involuntary stomach drop that the brain registers before the rational mind has time to interpret it. And for many passengers, it is the single most significant source of anxiety about air travel. The engineers who designed the Boeing 737 Next Generation series thought about turbulence in a specific, practical way, not as something to be accepted, but as a problem to be partially engineered out of the passenger experience. The most visible result of that thinking is the winglet, the upward curving tip extension that appears on the end of every 737 ENGs and MAX wing. Winglets became standard equipment on the 737-800 from around 2001, introduced through a collaboration between Boeing and Aviation, partners Boeing. They were initially justified primarily on fuel efficiency grounds, and the fuel savings are real. A Southwest Airlines 737-700 equipped with blended winglets saves approximately 100,000 gallons of fuel per year compared to the same aircraft without them, a figure documented in NASA's spin-off program. The fuel case alone made them worthwhile, but the winglet does something else. Something that matters just as directly to everyone sitting in the back of the aircraft. When a wing generates lift, the pressure difference between the lower and upper surface causes air to curl around the wingtip from below to above, forming a rotating vortex that trails behind the aircraft. This vortex is a direct consequence of how wings work and cannot be eliminated, but it can be reduced. The winglet intercepts the airflow at the tip, redirecting some of the energy in the vortex into a forward-acting component, and in doing so, reduces the strength and diameter of the vortex itself. A weaker wingtip vortex means less induced turbulence in the wake of the aircraft. For passengers on following aircraft, this matters for spacing and safety. But for passengers on the 737 itself, the reduced vortex strength has a more subtle effect. By changing the aerodynamic loading at the wingtip, the winglet modifies how the wing responds to gusts. The wing with a winglet behaves slightly differently in rough air than the same wing without one. The oscillations are damped more effectively. The ride is, in measurable terms, smoother. This is not the whole story of how the 737 manages turbulence. The wing itself on the Next Generation series was substantially redesigned compared to the classic generation. The NG wing has a greater aspect ratio and improved aerodynamic efficiency, but it was also engineered for better handling in varied atmospheric conditions. The wing flex, discussed in an earlier chapter, the designed-in bending that allows the wing to absorb rather than rigidly transmit aerodynamic loads, contributes directly to ride quality. When the aircraft hits an updraft, the wing bends upward, absorbing some of the energy before it reaches the fuselage. The passenger feels a softer version of what the unflexed wing would have transmitted directly. Boeing's Next Generation series also introduced improved yaw dampers, systems that automatically counteract the Dutch roll tendency that can make aircraft feel like they are swaying side to side in turbulence. The yaw damper applies small rudder inputs thousands of times per second, counteracting the tendency before it develops into perceptible motion. This is invisible to passengers. They do not feel the rudder moving. They simply do not feel the sway. None of these systems eliminates turbulence, and none of them is advertised on the boarding pass. You will not find a specification sheet for the 737 that lists improved ride quality through winglet vortex reduction as a feature. But the work is there, embedded in the geometry of the wing and the logic of the flight control computers, in the hours spent in wind tunnels and computational fluid dynamics simulations that produced the specific curves and angles of the NG wing. Every time you feel the aircraft absorb a bump and settle back to steady state, rather than shuddering through a sustained oscillation, some portion of that response is the result of engineering choices made by people who thought carefully about what it would feel like to sit in the back row during a rough approach. They thought about you, even if they never knew you. The descent begins quietly. The engine note changes first, a slight reduction in the low-frequency rumble that has filled the cabin for the past hour, barely perceptible at first as the auto throttle pulls back toward idle and the aircraft begins its long, gradual path downward. If you are awake and paying attention, you might notice a faint shift in the cabin pressure, a subtle sensation in your ears as the pressurization system begins adjusting to meet the lower altitude you are descending toward. If you are asleep, you will probably sleep through all of it. What follows over the next 20 to 30 minutes is a carefully managed sequence of aerodynamic changes, each one producing its own sound and physical sensation, each one moving the aircraft from its cruise configuration into the slower, higher drag configuration needed to land safely on a runway. The first significant change passengers notice is the spoilers. On the upper surface of the 737's wings, there are panels that can be raised into the airflow to interrupt the smooth passage of air over the wing. In cruise flight, these panels lie flat. In descent, when the pilots need to increase their rate of descent without accelerating, they raise the spoilers to add drag and reduce lift. The effect is immediate. A rougher, slightly louder quality to the ride. A modest bump as the aircraft's pitch adjusts, and a noticeable increase in the descent rate. From a window seat, you can sometimes see the spoilers raised, panels standing upright on the upper wing surface, disrupting the sleek geometry of the aircraft. Then come the flaps. The trailing edge of the 737's wing contains an extensive high-lift system, flap panels that extend rearward and downward from the wing's rear edge, increasing the wing's surface area and camber, generating more lift at lower speeds. The 737 NG has 7 flap settings, numbered 1 through 40, deployed progressively as the aircraft slows through the approach. Each setting produces a distinct aerodynamic change, and passengers feel each one as a small nose-up pitch moment and a change in the aircraft's drag level. The sound changes too, a low hydraulic whir as the flap actuators move, followed by a different quality of airflow noise as the extended flaps interact with the boundary layer. The landing gear comes next. On a normal approach, the gear is lowered somewhere between 10 and 15 miles from the runway, typically when the aircraft is configured with flaps at 15 degrees and descending through approach altitude. The gear deployment is the most physically distinctive event of the entire approach sequence. The pilots move the gear handle to the down position, and the two main gear bogies and the nose wheel assembly swing down and lock into place with a sequence of thumps and mechanical sounds that travel clearly through the airframe into every seat in the cabin. Passengers who are asleep sometimes wake at this moment. It sounds like something has fallen off the aircraft. It hasn't. It is simply three heavy assemblies of steel, hydraulic cylinders, and rubber tires rotating out of their wheel bays and locking into position under aerodynamic loads, ready to absorb the energy of touchdown. Below 1,000 feet above the runway, the autopilot is typically disconnected, and the pilots fly the final approach manually on most airlines. The aircraft is now descending at around 700 feet per minute, configured with full flaps and gear down, approaching the runway at roughly 140 knots, varying with aircraft weight. The engines are running at low power, just enough to maintain the approach path. The flight path angle is approximately 3 degrees downward, which is shallow enough to feel nearly level from inside the cabin, but steep enough to bring the aircraft from several hundred feet to the runway threshold in about a minute. Touchdown, when it comes, is another sequence. The main gear contacts the runway first. The spoilers deploy automatically to dump the remaining lift and press the wheels onto the ground, improving brake effectiveness. The thrust reverses open with a distinctive roar, redirecting engine exhaust forward to slow the aircraft. The auto brake system, preset before landing, applies hydraulic pressure to the wheel brakes at a calibrated rate, and the 79,000 kilogram aircraft that was suspended in air 2 seconds ago is now entirely on the ground, decelerating through 120 knots, 100 knots, 80 knots, slowing toward the taxiway turn-off speed of 30 knots with the unhurried confidence of a machine that has done exactly this at this airport or another one very like it thousands of times before. The runway is just the last paragraph of a very long story. Everything before it was the 737 doing what it was designed to do, quietly and precisely, from the moment the wheels left the ground. Rain changes everything about landing. The runway surface, which on a dry day provides abundant friction for braking, becomes a film of water over tarmac that reduces the coefficient of friction between the tire and the ground. In heavy rain, standing water can accumulate on the runway surface faster than the drainage system removes it, and an aircraft tire traveling at 150 knots over standing water can hydroplane, losing direct contact with the pavement entirely, the same way a car tire does on a flooded road, but at 3 times the speed. Boeing engineers designed the 737's landing gear and braking systems with these conditions as a primary design constraint. The aircraft has to be able to stop reliably in conditions that are worse than ideal, because commercial aircraft are not simply rerouted when it rains. Passengers have connections. Schedules have to be maintained. The system is built to work in the wet. The anti-skid system on the 737 NG and MAX is one of the critical components of wet runway performance. It works by monitoring the rotational speed of each individual wheel and detecting when a wheel is decelerating faster than the aircraft is slowing, which indicates it is on the verge of locking up and skidding. The moment it detects this, it reduces hydraulic brake pressure to that wheel just long enough to allow it to spin up again, then reapplies pressure. This cycle happens multiple times per second on each wheel independently, maintaining each tyre at the point just before it locks, where braking force is highest. It is the same principle as ABS in a car, but applied to a 79,000 kilogram aircraft, moving at speeds 10 times greater than a typical road emergency stop. On a dry runway at maximum landing weight, a 737-800 can stop from its approach speed of around 140 knots within approximately 1,600 meters using auto brake level 3 and speeds with thrust reversers deployed. This figure comes from Boeing's certified landing data. In wet conditions, the stopping distance increases, and pilots and dispatchers calculate their required landing distance against the available runway length before every flight to confirm the margin is adequate. The thrust reversers add to the stopping equation. Each engine on the 737 NGs is equipped with hydraulically operated translating sleeves at the rear of the nacelle. When the pilot pulls the reverser levers up after touchdown, these sleeves translate rearward, deploying blocker doors that redirect the fan airflow forward through cascade vanes on the sides of the nacelle, producing reverse thrust. The sound of thrust reverser deployment is the loud, rushing roar that passengers hear immediately after touchdown on most commercial flights. The engines briefly screaming in reverse before being brought back to idle around 60 knots ground speed. Boeing procedure calls for reverse idle by approximately 60 knots to reduce the risk of re-ingesting exhaust gas and prevent debris from being sucked into the engine from the ground surface. The speed brakes, the same spoiler panels used during descent, deploy automatically on touchdown when the weight on wheels sensors detect that the main gear has contacted the ground. Their function at this point is not drag alone. By raising up from the top of the wing and destroying the lift, they press the full weight of the aircraft onto the landing gear immediately rather than allowing the wing to partially support the aircraft during the ground roll. More weight on the wheels means more friction available for braking. The transition from flying aircraft to stopped aircraft happens through this sequence, each system engaging in its correct order, the whole coordinated by sensors and hydraulics that respond faster than any manual input could. When all of these systems work together under normal conditions, the landing roll is unremarkable, a controlled, progressive deceleration from touchdown speed to taxiway speed, taking perhaps 40 seconds on a long runway, less on a short one. Passengers feel the G-force of braking, modest on a gentle stop, firmer on a short runway, or in an expedited stop condition. The aircraft exits the runway and the engine noise drops to ground idle as the crew configures the aircraft for taxi. The whole sequence, from touchdown to runway exit, is over before most passengers have finished processing the fact that they have landed. But it relies on systems that took years to design, certify, and refine systems that must work correctly on every one of those 300 million landings. And across those 300 million landings, on wet runways and dry ones, in crosswinds and still air, at airports with long runways and airports where the margin is tight, the aircraft has reliably done exactly what it was designed to do. The part of the 737's story that most passengers never see happens at the gate, between flights, in the quiet before the next boarding begins, while passengers are collecting their bags or walking toward the terminal. A small ground crew has already positioned around the aircraft. The ramp agent has pulled the ground power unit into place. The ground engineer is conducting the transit check, a rapid but systematic walk around the airframe that covers every surface the aircraft has exposed to the atmosphere since it last left the ground. Tires are checked for cuts and correct inflation. Engine inlets are inspected for bird strikes or ingested debris. The landing gear doors are examined. Fluid levels are confirmed. The navigation lights are verified. This check takes perhaps 15 minutes on a normal transit, but its scope is comprehensive, and its purpose is to confirm that the aircraft that landed is as airworthy as the one that is about to depart. The 737 NG, by design, was built with reliability as an explicit engineering priority. Boeing integrated improved fault detection systems into the NG series and increased the mean time between failures of key cockpit and systems components by 62% compared to the classic generation. This matters enormously to airlines, because an aircraft that is not flying is not earning revenue. Every unscheduled maintenance event, every technical delay, every aircraft on ground condition represents a direct financial cost to the operator and a schedule disruption for the passengers booked on it. Boeing's reliability engineering on the 737 NG was not abstract. It was a commercial argument. This aircraft will spend more time flying and less time being fixed than anything that came before it. A typical Boeing 737 in commercial service accumulates around 3,000 flight hours per year, which works out to roughly 8 to 9 block hours of flying per day. This daily utilization figure means the aircraft is in the air for the majority of its working hours, and on the ground for the rest, turning around at gates across its network. The turnaround at a gate typically takes between 30 and 60 minutes for a domestic service, less for a very short-haul rotation at a high-frequency carrier, more for an international service that requires customs documentation and catering for a longer flight. Every 500 flight hours, the aircraft undergoes an A check, a structured maintenance event that takes between 6 and 24 hours, done at an airport hangar rather than a gate. Filters are replaced. Hydraulic systems are inspected and lubricated. The aircraft's emergency equipment, oxygen systems, escape slides, and life vests are all checked and confirmed serviceable. For a 737 accumulating 3,000 hours per year, this means an A check roughly every 6 weeks throughout its service life. Deeper checks follow on longer intervals. A C check, the heavy maintenance visit that requires the aircraft to leave service for around 3 weeks, occurs every 18 to 24 months. The C check involves up to 6,000 labor hours and includes structural inspections, system overhauls, and the replacement of components that have reached their life limits. Everything accessible is opened, inspected, tested, and closed again. The aircraft that comes out of a C-check has had every system it carries verified to be within specification. Every safety-critical component confirmed to be within its acceptable service life. Every structural area examined for fatigue or corrosion. The most comprehensive maintenance event, the D-check or heavy maintenance visit, occurs roughly every 6 to 10 years. At this point, the aircraft is effectively disassembled. Seats, overhead bins, galleys, toilets, and carpet are all removed from the cabin. The engines and landing gear are taken off. The outer skin panels are opened. Inspectors work through the structure, looking for any crack, any corrosion, any sign of fatigue damage that years of pressurization cycles and thermal expansion have produced. A D-check can cost several $1 million and take up to 100,000 labor hours. The aircraft that emerges from it, structurally sound and with all time-limited components renewed, can fly for another 6 to 10 years. All of this work, the transit checks and A checks and C checks and D checks, is done by maintenance technicians who work around aircraft all day and all night, at airports large and small, in hangars and on open ramps, in conditions that range from comfortable to distinctly challenging. Their work does not appear on the departure board or in the in-flight magazine, but every flight that completes without incident is, in part, a reflection of theirs. The Boeing 737 has been in continuous production since 1967. Every year of that production run, without interruption, aircraft have rolled out of Boeing's Renton factory and been delivered to airlines. No other commercial jet aircraft in history has maintained a continuous production run of comparable length. The number of aircraft built, 12,486 as of early 2026, represents something that is genuinely difficult to contextualize. It is more aircraft than all other wide-body commercial jets ever built, combined. It is roughly 4 times the total production of the Boeing 747. It is more than twice the number of Boeing 727s that were built, and the 727 was itself one of the most successful commercial jets of its era. The 737 is not just the most produced commercial jet in history. It is more produced than the next several most produced aircraft combined. Production has gone through four distinct generations, each one substantially different from its predecessor in engines, avionics, wing design, and systems, while maintaining the structural continuity that Boeing marketed to airlines as a key selling point. A pilot type rated on the 737 Classic can, after a relatively short transition course, fly the 737 next generation. A pilot qualified on the 737NG can transition to the MAX. This type rating commonality has significant commercial value to airlines because training costs are one of the major expenses in managing a pilot workforce. Boeing has used this commonality as a competitive argument against Airbus for decades. The Renton factory in Washington State, where 737s have been produced since production transferred from Boeing Field in 1970, is purpose-built for narrow-body aircraft manufacturing. It is the largest building by footprint in Washington state, and the production line that runs through it has been moving continuously, with some adjustments for rate changes and the grounding of the MAX between 2019 and 2020 for over 50 years. At its peak production rate before the MAX grounding, Boeing was delivering around 52 aircraft per month from Renton. That is more than one fully assembled, flight-tested commercial aircraft per day. The current production variant, the 737 MAX series, shares its fuselage cross-section with the 737-100 that first flew in April 1967. The cabin width, the door locations, the overhead bin structure, the aisle width, these are all constrained by the same 3.76 meter fuselage diameter that Jack Steiner's team set in 1964. Inside that tube, everything has changed. LED lighting, larger overhead bins that accommodate modern carry-on luggage, improved seat tracks, reconfigured air nozzles. The cabin of a 737 MAX 8 is a recognizably modern commercial environment, but the shell that contains it, the fundamental geometry of the cross-section, is the same one that Lufthansa crews walked through in February 1968. The 737 MAX entered service in 2017 with Malindo Air, a Malaysian carrier, as its launch customer. It brings LEAP 1B engines from CFM International, the same CFM partnership that has powered 737s since the Classic series, but representing the latest generation of high-bypass turbofan technology. The LEAP 1B is approximately 14% more fuel efficient than the CFM 56-7 that powers the 737 NGs, a savings that translates directly into operating cost reductions for the airlines that fly it. Each MAX aircraft in revenue service consumes substantially less fuel per seat per kilometre than the NG it is replacing. Orders for the 737 family continue to arrive. As of early 2026, Boeing has more than 4,000 unfilled 737 MAX orders in its backlog, representing years of future production. Airlines that need narrow-body capacity for expanding route networks continue to choose the 737 alongside its primary competitor, the Airbus A320neo family. The competition is fierce, and the order split between the two manufacturers reflects a genuine parity in the capabilities and economics of the two aircraft. The aircraft that was nearly cancelled in the early 1960s, that was held alive by a US Air Force training contract and the patience of Boeing's leadership, now has more than half a century of unbroken production behind it. The tail that once had to be assembled outside a factory door because the building was too small is now the tale of the world's most successful commercial aircraft program. Some stories take a long time to become what they are. Somewhere right now, a Boeing 737 is making its last scheduled flight of the day. It might be a late domestic departure running behind schedule, carrying the holdover passengers from a cancelled earlier service. The cabin full and the crew already past the midpoint of a long-duty day. It might be a red-eye route from a northern city to a southern one, the cabin half-dark, passengers distributed loosely across the seats, with blankets from the overhead bins and shoes removed. It might be a cargo conversion, a 737, with its passenger seats removed and its cabin floor reinforced for freight pallets, flying through the hours when passenger demand disappears. But the movement of packages and mail does not. The aircraft on this last flight of the day was, earlier this morning, flying in the other direction, or on a completely different route, or parked at a different airport, waiting for its day to begin. The 737 fleet does not sleep. Individual aircraft are rotated through maintenance windows and crew rest requirements. But the fleet as a whole is always moving, always somewhere in the middle of someone's day, even when it is the middle of someone else's night. The pilots on this last flight are tracking their duty hours carefully. Pilot rest regulations in commercial aviation are among the most detailed in the profession. The FAA's Part 117 rules in the United States and equivalent regulations in other jurisdictions prescribe maximum flight times, maximum duty periods, minimum rest windows between duties, and cumulative limits across rolling periods of 28 and 365 days. A pilot who has reached the end of an allowable duty period cannot legally fly another sector, regardless of airline scheduling needs. The system is designed to prevent the kind of fatigue accumulation that leads to degraded decision-making, and the records are tracked by airlines and audited by regulators. The flight itself on this last sector of the day runs the same checklist sequence as every other flight the aircraft has made since it entered service. The pre-departure checks are the same, whether this is the first flight of the day or the 8th. The before takeoff checklist asks the same questions. The climb checklist is completed at the same point in the climb. The automation does not know it is late. The aircraft does not know it is tired. The hydraulic systems that extend the flaps have no awareness of the hour. The anti-skid brakes that will stop the aircraft on the destination runway will function identically to how they functioned at 7 this morning. This is one of the less discussed sources of comfort in commercial aviation. The machinery does not accumulate fatigue the way human operators do. An aircraft accumulates structural fatigue in a measurable, trackable way, which is why flight cycles are logged and maintenance intervals are defined in terms of them. But the hydraulic actuator that deploys the spoilers performs identically on the 47th flight of its service interval as it did on the first. The engine that has been running for 6 hours today starts its next sector with the same performance margins as it had at first light. The degradation that happens to human alertness over the course of a long duty day does not happen to the systems that carry out the aircraft's physical functions. On approach to the destination airport, the city is spread below. Depending on the direction of approach, there are highways with thinning traffic, residential areas where most windows are dark, the bright perimeter of the airport visible several miles before the runway itself, the runway lights, the approach lighting system, the precision approach path indicator lights, telling the crew whether they are too high or too low. All of this is visible from the left seat of a 737 at 10 miles from the runway. The aircraft descends toward the lights. The gear comes down with its familiar thump. The flaps extend to their final setting. The speed bleeds off. The runway edge lights pass on either side. The main gear touches. The spoilers deploy. The reversers open, and the aircraft decelerates through the night toward the taxiway exit. Somewhere at the end of this taxi, a gate is waiting. Ground power will connect. The seatbelt signs will go dark. The boarding door will open. The passengers will walk off into an airport that is quieter than it was 12 hours ago. And the aircraft will be left with its maintenance crew and its own quiet systems, completing the last checks of the day. Tomorrow it starts again. We began in a quiet aircraft cabin just before pushback. The overhead lights dimmed. The hydraulic pumps cycling through their startup sequence. The whole structure of the aircraft settling into its vibration, that low, continuous hum that seems to come from everywhere at once. Everything that had come between that opening moment and this one was already present in the aircraft before a single passenger boarded. The 3.76-meter fuselage diameter, unchanged since 1964, the short landing gear, designed for airports that had no jet bridges, giving the aircraft its distinctive low profile. The forward-mounted engines pressed close to the underside of the wing, their flat-bottomed nacelles a visible record of 60 years of engineering compromise. The HEPA filters cycling the air every 2 to 3 minutes. The autopilot waiting to engage. The wing flex built into the aluminium structure, ready to absorb whatever the atmosphere offers. All of it was there before you sat down. And somewhere in the world right now, 1,250 other 737s are airborne, carrying their passengers through the same hum, the same pressurized air, the same slight altitude-induced drowsiness that has been settling over travelers in these cabins since February 1968. The aircraft that began life as a gamble, that nearly died in the early 1970s when Boeing received only 37 orders across its entire product line, that was held alive by a US Air Force training contract and the stubbornness of engineers who believed in what they had built, is now the most produced commercial jet in aviation history. More than 12,000 delivered. More than 300 million flights completed. The prototype N73700 is in the Museum of Flight in Seattle. It is smaller than the aircraft you flew on. The cabin is narrower in appearance, the windows slightly different. The interior decades removed from the modern fitted environment of the NG or MAX. But the cross-section is the same. If you stood in its aisle and then stood in the aisle of a brand new 737 MAX 8, you would be standing in the same diameter tube. The idea that Jack Steiner's team worked out in 1964, refined through 57 years of production, is still flying every 9 seconds somewhere above the Earth. The hum you feel right now, or the hum you remember from the last time you were in one of these aircraft, is the same hum that Lufthansa passengers heard on February 10, 1968, when the 737 made its first revenue flight from Hamburg. Not the same engines, not the same avionics, not the same cabin, but the same fuselage, the same geometry, the same fundamental vibration of a pressurized aluminium tube moving through the air faster than sound can carry the news of its passage. The aircraft is still working. The autopilot is holding altitude and course. The air is being refreshed every few minutes. The cabin pressure is maintained at an equivalent of 6,000 to 8,000 feet. The wing is flexing slightly under the aerodynamic load, absorbing what it needs to absorb, carrying you through the air with a steadiness that 57 years of refinement has made very close to perfect. There is nothing that needs your attention right now. The aircraft has the rest of it. The engineers thought about the turbulence. The controllers are watching the radar. The maintenance team signed off every system. The pilots are in the cockpit, or very close to it, and the autopilot is doing what the autopilot does. You are in the safest, most carefully maintained, most thoroughly tested form of transport in human history. You have been carried by it across the sky, and it will carry you the rest of the way. If you need to sleep, sleep. The aircraft knows where it is going.